All right, so the next topic we're going to talk about is what's called a queue. So unlike stacks, where I want you to think about pancakes, for queues, what I want you to think about is the Chick-fil-A in the Student Center. When you go and you place your order, you have to get into a queue in order to get your food. Theoretically, the first person in queue is the first person to get their Chick-fil-A. The last person into the queue is the last person to get fed. We are not going to debate the wonders of the Chick-fil-A. We are not going to debate whether it is always actually executed that way. But in theory, the first person in the queue is the first person to be served. This is true when you call into customer support and some phone number. You are supposedly answered in the order in which you were received. When you're getting to the grocery store and you're trying to check out, you are executed in the order in which you come in. Hopefully, you're not actually executed, because that would be terrible in a grocery store. Although the way grocery stores are. Anyway, moving on. All right, so queues are implementations of first in, first out. The last one that we spoke about, which were stacks, were last in, first out. Very different. LIFO versus FIFO, which is first in, first out. All right, in a stack, we talked about push and pop. Those are typically the verbs that are used for interacting with a stack because they make sense. You're pushing things in and you're popping things out. In a queue, because you're not doing exactly the same thing, we use the terms in queue and dequeue. When you are done with your grocery shopping, you in-queue yourself into the line for a checkout, and when you get to the front of said queue, you are dequeued and checked out. There's a lot of metaphors in here, but anyway, moving on. So in-queuing and dequeuing are the verbs that we tend to use. You may see a peak because it may be useful to see who is the next person to be executed, and so on and so forth. But in-queue and dequeue are the verbs that we're going to use here. So drawing this out in a picture, I want you to look at the implementation. In the case of the stack, you notice that everything happens on one side. Whether that side be the front or the back or the top or the bottom doesn't matter, but all the pushes and all the pops are happening on one side. In the queue, you will notice that they are happening on opposite sides. The new people go in on one side, the next person to be dealt with is pulled out on the other side. So again, it could be implemented either way, where front and rear are reversed. All that really matters is that you're in-queuing and dequeuing from opposite sides of the data structure. So here's an implementation of a queue, and we have an in-queue and a dequeue. This is again being done with a linked list. I didn't bother to re-implement this for you. You can absolutely copy this and paste it yourself. You see that we have a peek method, which simply returns head, which again is the front of the list's ID. We have an in-queue method, which we are going to put in at the front of the list. And then we have I'm sorry, I said that backwards, and that's why I paused. Sorry, we are in-queuing at the back of the linked list in this code, because I was actually reading the code and figuring out what it was doing, and we are going to dequeue from the front of the linked list, which is also why peek is looking at the front. That should have been a clue. All right, so in-queue is in-queuing at the back of the linked list. If the list is currently empty, then we know that the head is going to point to the new node that we're putting in. We stick all the data in the node, and we set head pointed to it. That means we now have a list with one item in it. If it is not, then we are going to walk our way down until the tail pointer is pointed to null. When the tail pointer is pointed to null, we're going to instead change that to tails next equals to the new node, which is going to insert it at the end, and then we're going to update tail to point to that node. Okay, now you might be thinking to yourself, what is tail and where did it come from? Which is also what I'm thinking, because it's the first time it was ever mentioned. These are not the greatest slides. Okay, when you create a linked list, we have talked about head. Head is wonderful. It's the thing at the front, and it points to this happy little list all the way over here. Okay, you put your numbers into the list or whatever data you're going to store in there. That's all makes sense. So hopefully none of that is new. The other thing that is often done is that you maintain another link or pointer, which we call tail. And it always is going to be linked to the last node in the list. There's nothing magical about tail, just like there's nothing magical about head. The tail pointer is going to be updated only when you add in a new entry into the list. So if you're always going to add at the back of the list, then you can simply say tail up, or tail.next is going to get a new node. You're going to put whatever data in there, and then you're going to change tail to be tail.next, which has the effect of the tail pointer always pointing to the right place. Okay, if you always do this, it just makes it so that you don't always have to start off at head and work your way down the list until you find the appropriate place, which is just a lot more work. The tail pointer just gives you immediate access to the back of the list so that you can throw new things in there. It's very helpful when you're dealing with a queue, which is what you're dealing with here. So to be clear, if this is an implementation of a queue, then effectively the order in which people are processed will be like this. The first person to be processed will be this person, the second will be this, the third will be that, and this will be the last person to be processed because, well, they were the most recent person to be put in. All right, so you will dequeue off of the front and you will enqueue onto the end using that tail pointer. All right, so that is a queue. So which data structure would you pick to implement a queue? Why? In making your choice, consider the data structure, which orientation you're doing, front or back. Is there a resizing overhead? And what's the big O of all of that? So your choices were doubly linked lists, array lists, arrays, singly linked lists. So what we have looked at so far is a singly linked list. And in the circumstance where we are enqueuing at the back and we have a tail pointer, this is order 1. It only takes one operation to do an enqueue for a singly linked list. Likewise, it only takes one operation to do a dequeue for a singly linked list because you just take it straight off the front of the list. If you reverse things and you enqueue at the front and dequeue at the back, as long as you still have your head and tail pointers, it's actually no worse. You'll just dequeue off the tail and you'll enqueue at the head. Works just the same amount of effort either way. Okay, is there a resizing overhead with a singly linked list? And the answer to that is no. The nice things about linked lists is that they dynamically grow and shrink as you get entries in and take things out. So our queue never has to change. We never at any moment have to say, oopsies, we're about to insert one too many, now we have to go resize the entire thing. So singly linked lists will have a big O of order 1 for enqueue, order 1 for dequeue, provided that you have a head and tail pointer. There is no resizing overhead, and it actually does not matter the orientation as to whether you work at the front or the back. A doubly linked list all works the same way. There's actually no advantage for a queue to doing a doubly linked list. It's the same as a singly linked list. You just got all these extra pointers which you have to maintain, but it's very, very doable. It'll still be order 1, and order 1, there's no resizing overhead, and the orientation still does not matter. Okay, so let's talk about implementing a queue in an array. All right, so a picture would probably be worth 1,000 of my words here. So I'm going to give you an array. I'm going to give you 10 cells. This is cell 0, 1, 2, 3, 4, 5, 6, 7, 8. 10 cells. Oh no, there was 10 cells. There were 0 to 9. What was I thinking? All right, there we go. Okay, so if we are going to implement a queue here, how would we do it? Well, presuming that we still have my magical current entries, current entries is currently going to be equal to 0. All right, so where are we going to stick the first person? Well, my guess would be that you're going to stick them in here. So this is not really very controversial. Enda is going to get added to cell 0. That will be true regardless of whether we consider this the front or the back. So the question is, when you go to insert the next person, where are you going to put them? So at this point, current entries is equal to 1 because I have actually added one person into the list. All right, if I enqueue the next person in here into cell number 1, that works, But there might be a bit of an issue here. When I go to dequeue the first person, I will have to shuffle everybody over one cell to the left, because when I dequeue, I'm going to dequeue out of cell 0, and then I have to move everybody all the way down the list, however many of them there may be, so that the first person is back in cell 0, the first person to be dequeued. If I do it the other way around, then the new person would go into cell 0, and then I have to move Enda to cell 1, which means that I would have to move whoever's in cell 1 to cell 2 and all the way down the list. So it seems like with a linked list, there's an immediate problem. No matter which direction that I try to do it, and to be clear, what I mean by direction or the orientation here is, are new people added after? Meaning, if this is cell 0, does the next person go into cell 1? Or does the next person go into cell 0 and I move everybody down? If the next person goes into cell 0 and I move everybody down, my in queue is going to be order n instead of order 1. My dequeue is going to be order 1 because I can just take them right out at the front. If I do it the other way around, then my in queue is going to be order 1, but my dequeue is going to be order n. So one way or the other, I'm going to have a lot of extra work that I'm going to have to do with an array. So you might say that for a linked list, for a queue, a linked list is going to be easier to implement just because of the nature of how you have a front and a back that immediately allows you to do things. There is a clever trick that you can use with an array, which is called a circular array. To be clear, there is no such thing as a circular array. But you see how I kept track of current entries? I can also keep track of first entry. All right, and what's happening here is, in the beginning, first entry, and I'm just going to clean up a lot of this crud, first entry and current entry immediately start off as being 0. All right, and life is good. I don't have anything in my array. All right, so I put my first person in, that's going to be Enda. All right, I'm going to change current entries to 1, and I'm going to leave first entry at 0. I'm going to put Fred in next. So Fred's going to get put into cell 1, and current entries is now 2, first entry is still 0. I'm going to add Jane. Jane goes into cell 2, so current entries is now 3. And now I'm going to dequeue. When I dequeue, I'm going to get back Enda because he was the first person put in, and dequeue is going to take him out of there, but at that moment I'm going to update first entry to be 1. So now my first entry is here, and my last entry, or the place that I'll put my next person, is here. So think of these as 2 links or 2 pointers that tell me which part of the array I'm currently using. The array is empty when first entry is equal to current entries, when the 2 have caught up to each other. I've dequeued everybody out of the queue and there's no one left in the queue, then my first entry and my current entries will be equal. When I put somebody new in, then my current entries is going to get further and further away. When I take somebody out, my first entry is going to move closer and closer to current entries. There is, of course, weirdness when you get to the end, because after you put in the 9th person, where does the next person go? Well, they actually go all the way back at the beginning, which is why it's called a circular array. I don't need you to spend too much time on this. I just want you to have an understanding that there is a clever way to solve this problem, which is a circular array. Overall, however, implementing a queue in an array is more painful than implementing it in a linked list, which is really why we taught you linked lists first, because it is possible to do it in an array, but it's not pretty. You're going to end up having to do this circular thing, or you're going to have to constantly shuffle everybody around in the array in order to make it so that it's correct all the time. Okay, and you could also do it in an array list, and the advantage of that is that it'll keep track of all of the array stuff for you. You just add and remove the appropriate entries as you go. So that's queues. This is the queue implemented as an array in Java, and that is the end of today's lecture. So let me review everything that we covered here very quickly from the standpoint of what is it that you need to know for a test. You need to understand what a linked list is. That was the last lecture. If you didn't understand that, please go back and rewatch the linked list lecture because the next lecture is going to be even more confusing. So make sure you understand linked lists first. Linked lists are simply a node. It has some data. It has a next pointer. Maybe it has a previous pointer. And they connect to each other all the way down a big long list of nodes. The last one is always going to have a null. The first one may be a null if there's nothing in the list, and eventually it will point to a node which will connect to another node, which connects to another node, and so on. That's a linked list. You can implement, today's lecture is stacks and queues. You can implement a stack or a queue using a linked list. You can also implement stacks and queues using arrays or array lists or just lists. It is possible in all of the above. It'll work in all of the above. It's just how much effort is it to maintain the structure in a way that when you do a pop or a dequeue, do you have to shuffle things around inside the structure? And it is important to understand that that shuffling is actually work that has to be done, which makes the algorithm less efficient. So, from an efficiency standpoint, putting things in and taking things out, you need to draw it out on a piece of paper and see how much work it is, just like I was doing on the little whiteboardy thing where I was moving things around and showing you. If you didn't get all of this, I would recommend rewatching this lecture, honestly, because there was a lot in here and there was a lot of different concepts that you've run around. We don't need you to know all of it. We're not asking you to implement all of it. We just want you to understand the ideas of how it all works and how it all connects to each other.